Let's talk a little bit about the conservation of momentum lab. Okay, what we're going to do here is we're going to look at a collision here. Okay, so that little bitty guy is going to run into that big guy there. Notice they're on a frictionless surface there. So on a frictionless surface, we believe that they're going to be hustling to shut my phone off, right? We believe on a frictionless surface, or just in general, right? But specifically isolated systems like this, right? If we calculate the momentum of that yellow cart before the collision, so like here, okay? If we calculate the momentum of just that yellow cart, and we calculate the momentum of both carts, conservation momentum states that the two momenta will be equal. Okay, so when we check out conservation momentum, conservation means equal. Okay, so this momentum here of this guy moving is the same as the momentum of both carts moving. That's the premise of what we're doing. Okay, now what we're going to do is we're going to look at this thing, and there's actually a tool we can use. Switch to my mouse, right? There's a tool we can use where we can click on the location. So once that thing leaves my hand like that, right, we can actually go in here and click on that thing. And I think I need to say, not 1 frame, let's try, I don't know, 10 frames or something, right? Okay, but I can click on that. And this thing, since it knows there's a meter down here, and I already told it that that's a meter, if I click on that thing, I think maybe I should do every 5 frames. But anyway, if I click on that, it's going to give me data of the position of this. From that, it can figure out the velocity, right? And if I know the velocity of that, I already know the mass of that. I've already measured that in the laboratory. I've also measured the mass of this. And so I can just keep doing this, right? And I can notice that the dots are a lot closer together now, right? I can keep doing that, and using this video analysis, I can determine what the velocity is before and after. Okay. Now, if we go to the particulars of this, right? Particularly the little cart here moving fairly fast, right, is before, and the big cart's not moving. Okay. So if I do this, I'm going to do the mass of, I'll call this mass 1, mass 2, right? Mass 1 times whatever that initial velocity is, right? The question is, does it equal, we don't know that it equals, right? Does it equal both masses together times whatever, so we'll call this V1, right? Okay. Does it equal mass 1 plus mass 2, right? Because they're stuck together, times whatever this second velocity is. That's the question, right? Now, understand that these momentums are not going to be the same because the mass has uncertainty, this velocity has uncertainty, you're clicking on the screen, right? There's inherent uncertainty in the data that you have. So what we have to do is we have to calculate a range of momentums here and a range of momentums here. Right? And the question is, do these two ranges overlap? And that's going to be the question, right? Okay, so for example, if we think the momentum here is, say, 60.1 gram meters per second or something like that, right? But it could have been as high as 65.3 gram meters per second, or as low as maybe, let's say, 56.2 gram meters per second. Let's imagine that this is our range from 56.2 to 65.3. If afterwards we say, oh, look at 62.5 gram meters, I'm just making up numbers here, right? Let's imagine we think it's, our best guess is this, our best guess after is this, right? We can't just say, well, look, that's not the same as this, right? What's the range of this? Well, already you can see that this falls between this and this. So yeah, they do overlap, right? So this could be, 67.5 could be the highest it could be, right? And maybe, I don't know, 58.3 gram meters per second would be the lowest, right? Well, clearly these ranges overlap, and we can look at examples of ranges that don't overlap. So that's the question, right? If you calculate the momentum before and the range of what the momentum could be. And I'll show you how to do that. That's what this lab is about. The question is, does it overlap? If it doesn't overlap, then momentum was not conserved. Okay, if it does overlap, then we haven't proven that momentum is conserved. We've just simply shown that we haven't disproven conservation of momentum. And that's all we really can do. In science, scientific models make predictions, and those predictions cannot be proven, but they can be disproven, right? If it makes predictions and those predictions don't happen, then the model isn't correct. Now, after a while, if we fail to disprove a model for a long, long time, then we probably surmise that it's probably correct, you know? Okay? This is how things go from a hypothesis to like a theory, okay? Anyway, there you go.